In this video, we are going to be taking a look at RLC series circuits. Now, when we previously looked at circuits, the circuits either had a resistor and an inductor or a resistor and a capacitor, but not all three at once, right? And in those instances, the RL and the RC, the resulting differential equation was a first order differential equation. Well, it turns out if you now have all three components, resistor, inductor, capacitor, we're going to end up having a higher order differential equation. And now that we have the methods for handling those, we'll be able to analyze these circuits, right? And these are considered fundamental circuits in electrical engineering, right? These are the building blocks for all the complex things that you can do in that discipline. So just as a quick reminder, let's draw a little schematic here. So we've got a resistor, we got our capacitor, we got our inductor. I'll just put my switch there, and then we have our voltage source, right? And again, for the voltage, so just the symbols R for resistor, C for capacitor or capacitance, R is for resistance, and then your L is for inductance. And then the notation for your voltage, it can either be V of t or E of t. V obviously for voltage, right? But E sometimes is used to represent an electromotive force, right? You know, you're moving those electrons. And so again, what are we interested in? Well, there are two fundamental things that, as far as differential equations is concerned, at this level, you know, we have the current at time t, right? So our current in the circuit at time t, and then also the charge on the capacitor, charge at time t, right? And we actually saw when we looked at the RC circuits, we actually came up with we were exposed to the relationship between the charge and the current. So the standard relationship is this, that the derivative of charge, that's your current. So the rate of change of charge is equivalent to your current, right? Now, even though this circuit now is just slightly more complicated than the RL and the RCs that we saw, it still abides by the same principles. And we have to thank Kirchhoff for those principles, and we know about the voltage drop. So let me just remind you, across a resistor, the voltage drop is simply your R times I. Across a capacitor, the voltage drop is 1 over your capacitance times your charge. And then across the inductor, the voltage drop is your inductance times the rate of change of current. So your L times di dt, right? And what Kirchhoff says is that the sum of these voltage drops must be equal to that your impressed voltage, right? So by Kirchhoff, when we add these all up, it better be equal to V of t. So let's write that down. So in fact, I'll start with this. So we'll have the L di dt plus the let's do the 1 over, well, let's do the R, let's do the R times the I, and then the 1 over C times the Q, and then that has to be equal to V of t, right? So that's again, this is by Kirchhoff, but when we look at this, so L, R, and C, these are going to be constants. So that's okay. But we have an equation that has essentially two unknowns. right? It has the I and the Q, and yeah, there is a derivative there. But remember, we want our ordinary differential equations to be in terms of just one dependent variable and one independent variable. And the way I can achieve this is by using this relationship between current and charge. So basically, wherever there's an I can replace it with dq dt. So this implies that L, right? So since there's an I here, right? I can basically think of that as taking the derivative of I, but I is the derivative of Q. So I'll do this, dq dt, and then plus R, and then again I'm going to replace I with dq dt, and then plus 1 over c times q, and then that's equal to v of t. So now if you think about it, what does this really mean, this expression? Well, I'm taking a derivative of a first derivative, so that gives us a second derivative. So here is the famous second order linear differential equation that describes the charge in an RLC series circuit, right? And again, this is an equation that all double E's know, and I'm assuming they love it because they use it. Well, some of them use it all the time. So this is the basic equation that we need, right? And so since it's second order, right, depending on what the L, the R, and the 1 over C, depending on how that plays out, right, we can handle it. And depending if we have an external voltage or not, the equation might be a homogeneous versus non-homogeneous. But again, we have all the techniques for handling this, right? So I mean, all we really need to do is just to do an example to illustrate this, because once you set up the differential equation, then you switch on over into solving mode, and then it becomes fairly straightforward. All right, so let's take a look at this example. So find the current, right, as a function of time, right, in an RLC circuit with, let's say, L is equal to 1 Henry. Our R, let's say, is 2 ohms. Let's say our capacitance is 0.1 farads. And then let's say V of t is 0 volts, right? And let's say assume the initial charge is 0 coulombs, and the initial current is, let's say, 2 amps. So is 2 amperes. All right. And again, what we want to find is the current. But very similar to what happened in the RC differential equation, where we had to find the charge first and then use that relationship that the derivative of charge is current, that's what we're going to also have to do in the RLC, right? So even though current is really this is what I'm told, right, is what we're interested in, or should be interested in, we kind of have to, using the differential equation approach, we have to go through our charge to get the current. All right, well, let's set up let's write down the IVP. Right, so our L is 1, So it's going to be d2q dt squared, and then our resistance, so plus 2dq dt plus 1 over 0.1. Now, 1 over 0.1 is 10, right? So then this is 10q, and then it's homogeneous because we have no external voltage, so 0. So there we go. So that's our second order. So this is now a Holdy, right? And then let's write down our initial condition. So the initial charge, that's Q of 0. We're told that there's no charge at time 0. And then the initial current, so I of 0 is equal to 2. But remember, we can state everything in terms of Q, because I is Q prime, or the derivative of Q. So I can restate this and say that, yeah, the derivative of my charge is equal to 2. And that way I have everything expressed in terms of the single dependent variable, right? So for our Holdy, all we need is the auxiliary equation. So here's our auxiliary equation. In fact, let me just indicate that. So the auxiliary equation is m squared plus 2m plus 10 is equal to 0. A quick check of this, if we check our discriminant, because it's always good to know, just kind of do this, and it's almost like you're forewarned as to what to expect. So we got b squared, which is 4 minus 4ac, so that's minus 40. So that is negative 36. So right away we have a negative discriminant, so we're going to end up having complex conjugates. Now let's set up our quadratic formula to find those complex conjugate roots. So m is negative b, so minus 2 plus or minus the square root. Well, I'll just go ahead and put the negative 36 under there. We already did that. And then this is all over 2a. So that's just 2. So let's see what we have. So we have negative 2 plus or minus. Now the square root of negative 36 is 6i. And then this is all over 2. So we end up getting negative 1 plus or minus 3i. So we can see our alpha, that's negative 1, and our beta is 3. So now, again, since it's homogeneous, we have what we need to write down. We can write down our basis and then our general charge function. So just kind of as a reminder, so this is the basis or fundamental set. It's e to the alpha t, and we're using t, not x, right? Because it's a function of time that we're talking about. So e to the negative t cosine of 3t, and then e to the negative t sine of t, right? So these are the two functions that essentially they span all the possible charge functions that would satisfy this differential equation. So let's write down our q. So our q of t in general form is that, now what we can do, let's go ahead and factor out the e to the negative t. So it's like this, and then we'll have the c1 cosine of 3t plus c2 sine of 3t. Right, so this is our general charge. Now, in order to figure out C1 and C2, we are going to have to use the derivative of charge. So let's go ahead and write that down, and then we will apply our conditions. Right, so Q prime of t using our product rule will be negative e to the negative t, and then I just bring down everything that's in the parentheses there. So we got that, so t2 sine of 3t, and then plus the first, which is e to the negative t, times the derivative of the second. So when I differentiate c1 cosine of 3t, I'll get negative 3c1 sine of 3t, and then a positive, when I differentiate C2 sine of 3t, I'll get a plus 3C2 cosine of 3t, and there we go. All right. So what do our conditions say? Well, our conditions say that when t is equal to 0, my charge is 0. So when t is equal to 0, q is equal to 0. So we have a 0 there. E to the 0 is 1. Cosine of 0 is 1. And then the sine of 0 is 0. So that tells us that C1 is equal to 0, right? Now, the other condition, our current, i.e. the derivative of charge, so when t is equal to 0, q prime is equal to 2, right? So when t is equal to 0, q prime is equal to 2, so I'm going to put a 2 right there. And again, I just fill in the blanks going from left to right with everything I know. So I'm going to have a negative 1 there. Since C1 is 0, it just eliminates that term. So I'm going to put a 0 there. The sine of 0 is also 0, so another eliminated term. And then plus, now this E is also equal to 1 at t equals 0. And then the sine again is of 0 is 0, so that term is eliminated. So the only non-zero term that we have left over here is the 3C2. So plus 3C2. So what does that mean? It means that 2 is equal to 3C2. Therefore, C2 is 2/3. So C1 is 0, C2 is 2/3. So now here's my particular charge function as a function of time. So it's e to the negative t. And then again, I'll do, so we'll have the 0 there. And then our C2 is 2/3. And then we'll have the sine of 3t. Right, and then if we distribute it now, so here's a nice way to write it. So it's 2/3 e to the negative t sine of 3t, and the units here would be coulombs, right? But that's, I mean, again, and I'm sure you can analyze the charge, and maybe in some instances that's your goal, but our main goal is to find our current. And then we just use the fact that I of t is the derivative of charge, like that. So then differentiating this function will give me the current. Now, again, we're going to have to use our product rule. Now, what you could do, technically, we've already differentiated the charge right here, but it's not in a nice simplified form. And the C1 and the C2 constants, they have not been plugged in yet. So you could go back here and then just plug in what we got for C1 and C2. Or if you prefer just looking at this and saying, you know what, I'm just going to look at this. Up here it's kind of messy. I'm just going to look at this and find the derivative. You can certainly do that. So what I will do is I'll bring down the 2/3. That's a constant multiple. And then inside I'll use the product rule. So negative e to the negative t times the sine of 3t. And then plus e to the negative t times 3 cosine of 3t. And then, so now if we go ahead and just, depending on how you want to do it, you could factor out the e, and then you have 2/3 e to the negative t. If you want to write what's in parentheses with a leading coefficient that's positive, write the cosine term first. So you'll have 3 cosine of 3t, and then minus sine of 3t. So that's our charge function, and then the units again would be amperes. So then at any given time we can sort of analyze this. right? And what's interesting in this particular case is that as t gets larger, these are sinusoids, so they would just oscillate, but then this term approaches zero. So what happens is over time, in fact, let's just go ahead and I will just state that as we wrap it up. So note, as t approaches infinity, the 3 cosine of 3t minus the sine of 3t oscillate indefinitely. Right, so it oscillates indefinitely. So that term, right, just goes between plus or minus 1. However, e to the negative t approaches 0. So it means that our current is actually transient, right? So we have a bounded factor here. This is transient, so it just nullifies everything. So therefore, I of t is transient. Basically, all the terms will approach 0. All right, and there we go. So once we, once we know the differential equation for the RLC circuit, we just apply whatever parameters are given in the question, and then, like I said, we get into solving mode. So that's what we did. Hope you enjoyed that. I enjoyed it. I'll see you in the next video for more solving. See you then.